Hello and welcome back to High Peak Education. I'd like to perform a sample calculation which is from a set of lecture slides which I did not perform then, and take a look at an example of Faraday's law. So let's have a look at this problem. It says an EMF is produced by rotating a 1000 turn 20.0 centimeter diameter coil in the Earth's, that is 5.00 times 10 to the minus fifth, Tesla magnetic field. What average EMF is induced if the plane of the coil is originally perpendicular to the Earth's magnetic field and rotated to be parallel to that field in 10.0 milliseconds? Okay, so let's write these various numbers down. It looks like capital N, which is the number of turns, is 1000. Now, by the way, turns is unitless. We also know the diameter of the coil is 20 centimeters. Let's convert that to SI units. That's 0.200 meters. But we're probably going to need the radius because I think we're going to need the area of the coil. So we need 0.100 meters. And we know the area, because it's a diameter of a circle, is going to be like pi r squared. We know the strength of the magnetic field. So the magnetic field of Earth, in this case, is equal to 5.00 times 10 to the minus 5 teslas. And we want to know, what is the average EMF? So what is the average EMF? Kind of like a magnitude of the average EMF. If that's induced in the plane, if the coil is originally perpendicular to the Earth's field, then rotated to be parallel in 10 milliseconds. So that means delta t is now 10 milliseconds would be 0.0100 seconds. Again, that's 10, 1, 2, 3, milliseconds. Okay, so I think that in order to get an EMF, we're going to have to use Faraday's law. So Faraday's law of induction. Okay, so let's write this down. So remember that Faraday's law of induction tells us that the EMF is equal to minus d phi sub b dt. That's the opposite of the time rate of change of the magnetic flux and notice that that's the EMF. Now, by the way, we really just care about the magnitude here, so let's just do magnitude, and then let's not worry about that minus sign. And also, let's approximate this EMF. What do I mean? Because we want the average EMF magnitude. So instead of writing this as a derivative, let's write it as a delta. So let's do delta phi sub b over delta t. Now, what is phi sub b? Well, that's BA cosine phi. Okay? So, notice that the magnetic field is going to change at least its perpendicular part of its area. Because I think that originally, let's just do a sketch here. It says the plane of the coil is originally perpendicular to Earth's magnetic field. So it's like this at first. And here's the magnetic field. And here's the area vector. And then over time, the magnetic field has not changed this direction, but the orientation of the loop has. So it's like that. So, since the area hasn't changed, let's say this is, again, approximately, the area is constant. So this is pi r squared, which is the area. But then we're going to have b cosine phi final, b final cosine final, phi final minus b initial cosine theta initial. Okay? Now, by the way, theta final, I think, this is the final situation, this is the initial situation. Phi final should be 90 degrees. We know the cosine of 90 degrees is 0. So then we just have this term going to 0. And then we just have b initial cosine theta initial. Again, we're just doing magnitude here. So let's not even worry about that minus sign here. this whole thing is divided by the time. Okay, so I think that, and then by the way, cosine of 0 degrees, this term is going to equal to 1. So I think in the magnitude, this will end up being, let's see, pi r squared b initial of the Earth, that is, because that's what it is, all divided by delta t. And let's put the numbers in. So this EMF average magnitude should approximately be, let's see, pi times the radius, that was 0.100 meters squared, times the magnetic field of the Earth, that was 5.00 times 10 to the minus 5 teslas, and then that all divided by delta t, and that's 0.0100 seconds. Okay, so let's get this value. So calculator's on. Let's go ahead and do alpha, get a stack, numerator over denominator. Let's do second pi times the radius squared, that's 0.1 squared. Okay, and then we'll do times 5 times 10 to the, that's second EE negative 5, and we'll divide that all by 0.01. Okay, so let's write this down. 1.57 times 10 to the minus 4. So this is approximately 1.57 times 10 to the minus 4 volts. Remember, because it's an EMF. So we used Faraday's law of induction to calculate an EMF in a loop that gets rotated in Earth's magnetic field. By the way, this is smaller than millivolts. This is like 0.157 millivolts. So it's a pretty small voltage. Earth does not have an extremely large magnetic field near the Earth's surface. So thank you very much for your attention. Please smash that like button if you enjoy this content. Please share this video amongst your social networks and subscribe to the channel to grow the channel. I look forward to your comments on the video, and I will hope to see you in the next video.